Here we will solve a least square approximation problem using the singular value decomposition. So let's say I have the following matrix: 0, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2. Okay. So that's my matrix, and my two unknowns are in the vector beta 1 and beta 2. So that's the two values I want to determine the most accurately possible. And the values I have are square root of 2, 1, 1. Okay, so that these are the values, and now I want to approximate them using the matrix A and the values of beta that I have to determine. So, and I will solve that using the singular value decomposition. So just first recall that to solve that with the SVD, so singular value decomposition, I need to find the vector D, which is defined by U transpose B, and then the solution of the problem will be given by so beta is equal to the matrix V times the pseudo inverse. So remember, it's the sigma hat inverse, where you remember that your matrix sigma contains the singular values in the diagonal, and the inverse basically means you, in the diagonal, instead of having the singular values, you have 1 over the singular values. Remember that. And the hat basically is you cut some rows of sigma so that you can multiply it with V. Okay? And also sigma, this pseudo inverse is multiplied by D0. And also remember that basically D0, it's the same procedure. You cut some rows of D so that you can multiply it with this pseudo inverse. So with this sigma hat inverse. Recall that. So I will find, first I will calculate A transpose A. Okay. So it will be 0, 1, times 0, 1, so you should get that. Okay, and so if I multiply that, I should get the following. So you can multiply it, it's just computation. You should get 1002. Okay. Now I will find the eigenvalues, and so here we have a diagonal matrix. So you can already see that the eigenvalues are 1 and zeros. Remember, the eigenvalues of a diagonal matrix are the entries on the diagonal. I will say that lambda 1 is equal to 2 and lambda 2 is equal to 1. Why? Because remember, the singular values will be defined by the square root of the eigenvalues, and you, in the matrix sigma, you have to put them from the biggest singular value to the smallest. Okay, so sigma 1 will be the biggest, and sigma 2 will be the smallest here, because you will have two eigenvectors, or two singular values, and so I already put them in the good order. Okay. Yeah, and now because this is A transpose A, so I can find the eigenvectors of that, and they will be contained in the matrix V. Okay, remember, the eigenvectors of A transpose A will give us the vectors of V. So this will give us the vectors of V, and A transpose will give us the vector of U. Remember that. So for lambda 1, so which is 2, if I find the eigenvectors, I should get that, and so I should get 0, and so x2 is free, so it can be everything, and x1 is equal to 0. Okay, remember, you solve that, that should be equal to 0, 0. Remember, this is just how you find the eigenvectors. And so our eigenvector v1 will be, so x1 is 0 and x2 is 3, so you choose 1. And so it's already a unit vector. Now to find v2, we'll get 1 minus 1, 0, 0, 2 minus 1. Then I will get 0, 0, 0, 1, and that should be equal to 0. So I get that x1 is 3 and x2 is 0, and so v2 will be 1, 0. And so it's already, here it's also a unit vector. So I have v is equal to first unit to v1, so 0, 1, and then v2, 1, 0. Okay. Now I could find the eigenvectors of A transpose. Remember that the eigenvalues for A transpose A and A transpose are the same. So I could find the eigenvectors by A transpose, or I could use the relation. Remember that Ui, so the ith U vector, is given by 1 over sigma I times the matrix A times Vi. Similarly, if we knew the vectors of U but not the vectors of V, the formula would be the ith vector of V would be equal to 1 over sigma I times A transpose, be careful, times the ith vector of U. Okay? So, we can say, so our singular value is sigma 1 is the square root of the first eigenvalue, so it will be the square root of 2, and sigma 2 be the square root of lambda 2, it will be 1. Okay. So I know that u1 will be 1 over square root of 2 times a which is the following, times v1 which is 0, 1. Yep. And so I get that this is equal to, if you do the computation, you should get 1 over square root of 2, 1 over 2, and negative 1 over 2. Okay? And u2 would be equal to 1 over sigma 2, so 1 over 1. So I don't even need to write it. Okay? Times a okay, times v2, which is 1, 0. And so, if you calculate that, you should get 0, 1 over, let me write that here. You should get 0, 1 over square root of 2, 1 over square root of 2. I hope you can read it. Okay, and now I need to find u3 because remember the singular value decomposition is A equals u sigma v transpose. Sigma is of the same size as A, so A is a 3 by 2 matrix, so sigma is also a 3 by 2 matrix. Okay. So we have 3 rows for sigma, and then we need to multiply it with u. So u should have 3 columns, so we need a third vector. Okay, so u should have 3 columns, so 3 vectors. Okay, otherwise we can't multiply sigma with u. Okay, and for that you can, the goal is to find a vector u that is orthogonal to the 2 others, and also so orthogonal and also of length 1. But if it's orthogonal, it should be of length 1. Okay, so you can use Gram-Schmidt for that. I think you know the Gram-Schmidt process. Otherwise, there are videos about it on YouTube. Or here, because we are in 3 dimensions, we can use the cross product. So we know that u1 cross u2 should get this a vector that is orthogonal to the 2 others. Because you can use that because you are in 3 dimensions. Okay. So if you calculate it, you should get that u3 is equal to the following: 1 over square root of 2 minus 1 over 2 and 1 over 2. Okay, so here I used that trick with the cross product because I am in 3 dimensions. Otherwise you would need to use Gram-Schmidt, or maybe there is another method, I don't know. But so you could find a vector that is orthogonal. So now I have my 3 vectors, and so u is equal to these 3 vectors, so I will rewrite it. 0. Okay. Now, remember, we need to find the vector D, which is equal to U transpose B. So we know B. Recall B is equal to square root of 2, 1, 1. And U transpose, you just transpose it. And so if you calculate D, you should get 1 square root of 2, 1. Okay, now remember the solution of our problem will be beta equals V times sigma hat inverse times D0. First, let's write our matrix sigma, or original matrix sigma. It has the same size as A, so a 3 by 2 matrix, and the two singular values on the diagonal will be square root of 2 and square root of 1, which is 1. Okay. Now, the inverse of that will just be, remember, you take 1 over the singular value. Okay? So 1 over 1 is 1. And so the hat just means that you should be able to multiply it with V. But V is, I didn't write V, so, yes, it's 3. Let's just rewrite it. V is 0, 1, 1, 0. So it's a 2 by 2 matrix. So it has 2 columns. But we need to multiply sigma with V. So sigma should have 2 rows to be able to multiply it with V. Okay? And so we can cut the last row. So our sigma hat inverse, which is also called the pseudo inverse. I don't know why, but it's also called the pseudo inverse. So our pseudo inverse will be 1 over square root of 2, 0, 0, 1. Okay? And now also, remember we need to multiply D with sigma. But our D has 3 rows, but sigma only has 2 columns. So we will need to so remember D is given by the following. We will cut the last row, basically, and so D0 will be 1 square root of 2, and remember D is defined by D0, D1. D1 would just be equal to 1. Okay, it would be the third component, but we don't need D1, we never use it, so yeah, I won't write it. Okay, so now I have the pseudo inverse. I have D0, I have V, so I can solve that. Beta is equal to V sigma hat inverse D0. And so this is equal to, so V is 0, 1, 1, 0. Sigma, or pseudo inverse is 1 over square root of 2, 0, 0, 1. And D0 is 1 and square root of 2. Okay. Now if I multiply that, I get square root of 2, 1 over square root of 2. And so I get that beta 1 is equal to square root of 2, and beta 2 is equal to 1 over square root of 2. Okay, so these are the two unknowns, and so these are the best approximation I can use to solve my least square problem. Okay, so remember, just first you do the singular value decomposition of A. So you calculate A transpose A or A transpose. You find the eigenvalues of A transpose A or A transpose, which are the same eigenvalues. Then you find the eigenvectors. The eigenvectors of A transpose A are the eigenvectors, will be the vectors of the matrix V. And the eigenvectors of so let me write that to give you, if you find the eigenvectors, you find V, and A transpose, if you find the eigenvectors, you will get U. So you have to make sure that the vectors are orthogonal, and so they also have to be of length 1, and then if you don't have enough vectors for U or maybe V, you need to find other vectors that are orthogonal to the other vectors. If you are in 3 dimensions, you can use the cross product. Otherwise, you can use Gram-Schmidt. And then you have the relationship to find, if you found the vectors of V, you can find the eigenvectors of A transpose to find the vectors of U, or you can use that relationship that Ui is equal to 1 over sigma I times the matrix A times Vi, and the inverse would be Vi is equal to 1 over sigma I times A transpose times Ui. Okay. So you find your singular value decomposition. The singular values are put on the diagonal in sigma, and they are the square root of the eigenvalues. Okay, so sigma E equals the square root lambda E. And then to solve the least square problem, you find D equals to U transpose B. Yeah, and then you find the pseudo inverse. Okay. And so on. And you cut some, so if there were zeros here, you cut the rows, so you can multiply then with V. And also you find D0 by cutting the rows of D in such a way that you can multiply it with sigma. Okay. And so your best approximation, so here we used beta as the values we search. You can use another letter. The best approximation will be given by V times the pseudo inverse times D0. Okay. So yeah, thanks for watching.